Hello, and welcome to another Applied Flow Technology webinar. I am your host, David Despars. Today we're going to be talking about a topic that I call when minor losses aren't so minor. Today's agenda is going to be all about minor losses. We are going to touch on major loss and minor loss equations, get a feel for those back from our junior level college days, trying to refresh those in our minds. We're going to dig into the minor losses of junctions, common ones such as loss coefficients, CV, KV values, resistance curves, and many more. We're going to see how we can apply those minor losses in pipes through the fittings and losses option. And then we're going to discuss and think about some more nuanced questions such as how do minor losses get affected in laminar flow? What about compressible flow? And what about transient flow? So without further ado, let's get started. Let's start with the loss equations. Major loss, as we know, is the pressure or head loss that is attributed to the pipe wall, friction, and fluid. These are pretty common. It's going to be your delta P is equal to the frictional factor times the length over diameter times 1/2 density velocity squared. I like thinking in terms of pressure, but I know there's a lot of people that like to think in terms of head, so you'll see those equations here as well, the delta head variation. Refresher of friction factors. Friction factors are going to be a function of your Reynolds number, basically your inertial versus viscous forces. It's going to be in relation to the wall roughness value and the pipe diameter, as well as if you are in the laminar or turbulent region. You'll see that kind of graph. That's the Moody diagram that we're familiar with, determining the friction factor of your flow. Minor losses, on the other hand, these are going to be the pressure and head loss attributed to components in the flow, such as valves or bends. This is going to be due to either the turbulence within the valve or the component itself. This is going to be due to the momentum changes, such as if you have a bend, a 90-degree bend, there is a resistance to turning that momentum 90 degrees. And that is going to be captured by the minor loss, pressure drop or head drop. Those equations are there for you. Delta P equals the loss coefficient times 1/2 density velocity squared. Your loss coefficients, K, sometimes this is also written as a lowercase chi, depending on what literature you're reading. This is going to be a unitless value. It is proportional to the velocity component of the Bernoulli equation. That is because the faster the flow is moving, the more loss that will be occurring. Major and minor losses get their name from which is often considered more significant to the pressure loss. Major losses being that frictional component. A lot of people will say that the friction is all you need to worry about, and others will say the minor losses, they're small and less significant. The purpose of this webinar is going to be discussing these minor losses and then also kind of saying perhaps these component losses are more significant than we are led to believe, and in what situations are they need to be more considered. So looking at minor losses within junctions, we have our general minor loss formats. This is going to be K flows into or out of pipes. Your user specified K values, CV, KV values, etc. And then we're going to also dig into a few special loss options such as area changes, bends, everyone's favorite, simple and detailed T's. Starting with the K flow into out of pipe. This is going to be available in your branch junctions, your reservoirs, and your assigned pressure junctions. First, to kind of clear up some confusion about which value do you need to enter. Looking here at this image on the right, we have a pipe direction going to the right, we have a flow direction going to the right, so they're all in one direction with each other. The software will apply your K into pipe, being the flow into the pipe. Trying to be as self-explanatory as possible there. And then it will be using the K out of pipe for any flow leaving the pipe. Fathom, Arrow, Impulse, all of our software, we give you the choice to decide which is the pipe direction. This is going to be a datum, basically saying the direction you believe the flow is going. But it can still calculate for you a reverse flow situation. And it will use the appropriate K values in that situation. So if we see here we have reverse flow, it will now be using K into pipe from the right hand side and K out of pipe on the left hand side. To kind of give a little bit more formalized way to look at this, if we have two pressure points, pressure 1 and pressure 2, pressure 1 will have the minor loss associated with the flow entering the pipe, coming to the pipe inlet, the pressure drop that is associated with the friction along the length of the pipe, and then the pressure loss of the flow leaving the pipe into whatever is pressure 2. So there's our equation for us, taking into account both the inlet and outlet minor losses as well as the important major frictional losses. Let's look at the user-specified loss K factors. This is available in practically every junction that represents hydraulic loss. You'll often see, for example, like if we're in a screen, it will be in the loss model tab under a loss model option. So you select K factor and then you will enter in the value accordingly. There's some special cases such as your assigned flow junctions where it will appear instead on the optional tab, but they're everywhere. And it's just going to follow that simple minor loss equation. Delta P is equal to the loss coefficient times 1/2 density velocity squared. So and the reason that it is part of practically every hydraulic loss is just it's so generic and convenient. It's very easily applicable across a range of hydraulic problems. Let's take a step deeper into reservoirs. Reservoirs have a little bit extra entrance and exit loss options. So for example, they have an additional type option when you are on the pipe depth and loss coefficient tab. Sharp entrances, this is going to be a K equals 0.5. All of these values here are coming from crane hydraulic data. So if you open up your crane technical paper 410, you'll see these values. Reentrant is going to be somewhere between 0.5 and 1, and that is going to be dependent on how deep into the reservoir this reentrant pipe is. As a kind of a medium factor, we put 0.78 from that crane technical paper. And then rounded entrance will have a K that is a function of the radius over diameter. So you'll see that changed accordingly. And then once you get to a certain point, such as radius over diameter of 0.15, that K value will stay a constant 0.04, the least amount of loss that you could experience entering the pipe. A curious note to point out is the K flow out of pipe for all of these options is going to be a steady 1.0. And I put a little asterisk here. K equaling 1 is quite often used and quite often found for any kind of exit flow conditions. This is useful for when you are discharging the pipe into the reservoir either below or above the liquid surface level. It's going to be a K factor of 1. And this is because all kinetic energy from that outlet of the pipe and our point infinitely far within the reservoir of fluid at rest, all that kinetic energy between these 2 points is completely lost. And that's accounted for by K equals 1. It's not always K equals 1. Sometimes it will be slightly less or slightly more depending on the conditions of those exits, whether you're exiting into a river that is moving or a mixing vat. All kinds of different variations, but it is very closely attributed to 1.0, hence why we have it here. You'll note that in the custom option, our default option, we don't just assign K equals 1, we assign K equals 0. At AFT, we don't want to assume your inputted values. We don't want to make engineering determinations without you knowing what they are, and we want you to be making those decisions for yourself, whether they are needed or not. So the defaults will be equal to 0, but quite often we find that the exits are going to equal 1. So here comes up a very interesting question, one that we kind of see time to time within our support inbox. Does it really matter if I use entrance and exit losses? And I'm going to give you the wonderfully ambiguous, non-satisfying answer of it depends. It depends on a lot of things, and we'll see that here in a few moments. But I'm going to repose a question back to you. How much variation in flow pressure and velocities is acceptable to you from your real system and your model system? In this example, this thought experiment, we're going to take 2 simple reservoirs, a simple model of 2 reservoirs and 1 pipe. This is the simplest Fathom model you can make. And we're going to introduce a sharp connection, K equals 0.5 for the entrance, K equals 1 for the exit, to one set, and then we're going to attribute lossless 0 and 0 to the second set. What we can then do is vary the length of these pipes until we see the velocity differ by some percentage of concern. And that percentage of concern or percentage of difference is going to be shown up by this equation right here. So what if we say that our percentage of concern is 5%? Why 5%? It's a nice number and it's easy to think about. You would need to think for yourself if that's a worthwhile value. Maybe to you, 1% difference is reason for concern. You need to be able to determine that for yourself, but for our thought experiment here, we're going to stick with 5%. I've already kind of done the math for you, and it all gets jumbled into this graph right here. That if we have some pipe length versus some pipe diameter, there will be an intersecting point that says at this pipe length and diameter, the differences in velocities are going to be 5%. Let's consider a 4-inch pipe. I like a 4-inch pipe because it's roughly the size of a fist. Most people can fit their arm into a 4-inch pipe, so it's pretty easy to visualize. And then if we take that 4-inch pipe, and it is shorter than a football field, thankfully American football and international football fields are almost the same length, so just think football field. If your 4-inch pipe is shorter than a football field, the minor losses could impact the velocities by more than 5%. Football field's not that long in the grand scheme of things. So when looking at this graph, you can say, okay, shorter than a football field for that 4-inch pipe, the entrance and exit losses will have a greater impact on the flow than 5%. And then on the other side, the entrance and exit losses will have less of an impact. We can also see that if we were to increase the pipe diameter to a larger diameter, those larger diameters will be more impacted and susceptible to minor loss changes as well. And you can build all of this within a Fathom model as you please. So here in my example, opening up the reservoirs, give it the liquid surface pressures and elevations that you need accordingly, giving it the K factors accordingly. This is where you would change it from your custom to sharp. And then all you do is you just keep changing the length of the pipes until the velocities. We have our calculated velocity terms here, such as 32 feet per second for the lossless and 30.4 feet for the one with entrance and exit loss. Plug that into our equation. That's where we get our 5% difference from. So if we were to stick in our minds to a single pipe size, let's stick to the 4-inch pipe. I've made an example where we have a 10 meter, 100 meter, 1,000 meter pipe. We can come in here and show that the lossless versions and the sharp edged entrance exit versions, their velocities will differ by a different amount of percentage. That 10 meter pipe, there will be a 32% difference. 100 meter, about a 4.4% difference, and that 1,000 meter, 0.443%. So the longer the pipe, the less difference there will be in the velocity differences, which is kind of expected. The more frictional effects that the pipe can impose on the fluid flow in relation to the minor losses, that's the correlation that we are seeing here. Let's see a different graph here. Back to our idea. Shorter pipes are more susceptible to changes in velocity. If we graph a 2, 4, 6-inch pipe over a range of lengths, we can see they all tend to get close to 0% difference the further they go away. But the shorter they become, such as when we're looking at a 1 meter pipe that's 4 inches in diameter, those velocities differences are going to be greater than 100%. And so seeing that there is a much more significant change in those velocities at the shorter lengths. So back to the original question. Does it really matter if I use entrance and exit losses? Still the ambiguous, maybe, maybe not. You need to determine for yourself whether they're important. Is your pipes long enough or short enough that it has an effect? Maybe what you would want to do is make two scenarios, and you make a scenario with the minor losses and a scenario without, and you compare and you say, is the percentage difference enough that I should keep it with or without? I'll be honest, I think that's way too much thinking, especially because it is really easy to include the minor losses. When we are sitting there setting up our model, we're looking at our reservoir, we enter our liquid surface elevation, our pipe depth elevation, our liquid surface pressure. It's very easy to just go to one more tab, think for a moment what kind of entrance or exit this will be, and apply appropriate K factors to just have really the most detailed model that you can. It's a good bang for your buck. And then you don't have to think about it too much. Let's step into another, back into our minor losses, other forms. We're going to look at flow coefficients for valves. These are our CV and KV values. These are going to be available in practically any valve within our software. Here's the equation for them. CV is going to equal the flow rate times the square root of the specific gravity, taking that density of the fluid you're working with into consideration, over the change in pressure. Now, CVs are very particular in how they're measured. If you go and read in detail, like they say you have to use 60-degree Fahrenheit water with the flow, and then there's a 1 psi pressure drop between the inlet and the outlet, and then you measure the flow rate. There's very specific ways that they go about measuring these CV values in the valve manufacturers. One thing to keep in mind, though, that the CV is unit specific, using those gallons per minute and PSI. If you're looking at kV values, those specific units are going to be your cubic meters per hour and bar. And because we're using very specific units for CV and kV, we can have a correlation between them, a conversion formula shown here. Entering them is pretty straightforward. You can either do it in your user specified, maybe you're doing it from a characteristic where you have your CV, kV value. Control valves. Control valves are the next step. This is where the control valve junction will vary the loss until a set point is reached. And you have a couple options for your set points. You can determine you have a set upstream, downstream pressure, maybe you have a design flow rate or a design pressure drop. What the control valve will do is continue to vary the loss until it meets that set point, so long as it's physically possible. You can also specify a fully open loss to be either lossless or a defined amount, such as if you know that an open valve has a CV of 600 and it's not just infinite, set it to 600. That's available for you. The nice thing about control valves is the moment you give it a set point and it finds the loss for you, it will represent those, it will give you those in the output in terms of K, CV, and KV values, which you can then turn around and use to size a real valve if it wasn't actually a control valve. We'll see an example of that in a moment. Resistance curves. These are very flexible in defining hydraulic loss. They're available in a whole slew of options here just because they're so general and flexible. What a resistance curve is going to do is it's going to take your raw data, you're going to go to your enter curve data, give it a table. Let's look at an example here. You're going to select resistance curve, enter resistance curve data. It will give you a table where you will enter in the volumetric flow rates versus either pressure or head drop. It will take that data for you and convert it into a polynomial. Such as this one here. And you can do up to a fourth order polynomial. Delta H, delta head, is going to equal that polynomial. One thing to keep in mind about resistance curves, it's very flexible. I mean, you can have up to 100 data points and it will make a curve fit for you. Once that polynomial is created, that is what the solver is going to use. So it is a middleman. You're going to take your raw data, makes a polynomial. That polynomial will be used for all solver outputs. And so if you were to go back and look at your polynomial or your raw data, you will see that your outputs line up with the polynomial, not the raw data. That's intentional. That's partly for the resistance curve itself. So you may want to also make sure that your polynomial well defines your raw data. That's something you need to be able to say. Equivalent lengths. These are a very interesting one. They're going to be available in valves and pipe fittings and losses. They're going to convert the pressure loss that would be seen in that valve or fitting into an equivalent length of pipe. So if it takes 50 feet of pipe to equal the pressure drop, that is your equivalent length. Here's the equations for you if you wanted to look at them, but often these are coming from, are used in conjunction with a table. A table already has the equivalent lengths for particular valves or fittings already kind of predetermined and generalized for you. All right, so how can I swap between the different loss methods? We alluded to that within the flow control valve. The key concept here is if a system is hydraulically equivalent, and what I mean by that is the boundary conditions, the pipe layout, the input parameters, and especially the hydraulic losses within your system are all the same, then the K factor, CV, KV, resistance curves, they can all be used interchangeably because it is a hydraulically equivalent system so long as they're converted properly. So let's take a gander at that. Here in my model, I want the flow rate between these two reservoirs to be 50 gallons per minute. So I enter it accordingly. Press OK, go run, and I can come to my output for my flow control valve, and it will spit out for me the loss required to reach that set point, 50 gallons per minute. And we can see we have a KV, CV, K, and a head drop across that valve. If we turn around and we take those values and enter them right back into the valve, such as this CV right here, I just give it the CV 34.72, it will produce the exact same CV, KV, K factor, volumetric flow rate, and head loss. That is because these systems are hydraulically equivalent. These pipes are the same. The reservoirs are the same. The only thing changing is how am I representing this loss, and the hydraulic loss is all the same. So this is a good way to be able to size your valves, is pick a flow control valve, pick a set point, size your valve, and enter it accordingly. We can look down this table and say if we used KV, same values. We use a K factor, same values. Resistance curve, this is how if you wanted to use a resistance curve option, take the flow rate, 50, take the delta head, 4.787. I would go to this resistance curve, I'd enter in my flow rates, 50, the head, 4.787. From a single data point, pressing fill as quadratic, it will make me the polynomial that is equivalent to that K, equivalent to the CVs. And so now I have 50, 4.787, generate your curve fit, run the model, and they're all still the same, hydraulically equivalent. And I don't expect you to go do this, but if you were curious, I could go for that equivalent lot length equations I showed. I could calculate that the pressure drop is equivalent to 102 feet of pipe. So pretty straightforward, and that is demonstrating that they are hydraulically equivalent, and you can capitalize on that concept to be able to size your valves and size your system accordingly. CDA and CD values, coefficient of discharge area. These are available within relief valves, orifices, venturis. I see them a lot if you're dealing with air entering, exiting systems. The definition of that CD, coefficient of discharge, is going to be equal to the mass flow rate over the density, velocity, area of the restriction that you're working with. These tend to be within a range of 0.6 and 0.85. They could be outside them, but they just tend to fall within that range. And an interesting note here too, while we're talking about CDs and CDAs, within Aero, there is also the option for a CDA for sonic choking optional. That's the way you'll see it. It's optional, but if you are concerned about sonic choking happening at a valve, at orifices, then you need to enter this value. That is because Aero it will calculate and say, I believe there is sonic choking, but I don't know for certain unless the user enters this value. You enter the value, and then it can say for certain, yeah, sonic choking, you are constricted to Mach 1 at that orifice. Everyone's favorite, T-junctions. We have simple and detailed models, and they can tend to be quite wacky, shown by our little rotating T-junction here. We have a simple and a detailed model. Simple is going to be lossless. There is no hydraulic loss across it. And then there's going to be a detailed variation where the loss of the 3 connected pipes will be based upon the flow velocity for that pipe. This is really good because it will include the returning resistance. This is going to be based upon Idle-Chick and Miller hydraulic correlations. Question we get: detailed T's are superior, right? It says it in the name. Detailed. It's going to be superior. Another unsatisfying, perhaps not. I do want to point out the curiosity here. If we have a very simple flow in to header going down 3 lines with the simple T, I would expect, if these were equivalent pipe lengths and diameters, we would expect to see greater flow in the first pipe, and it will decrease to the end to the last pipe. However, if we return around and you say we want to use detailed T's, there is going to be more turning resistance in the first than there will be in the second. So we should expect, not always, but there's just a trend that we see, more flow going down the final header than the previous 2 lines. So this gets back to our topic about the reservoirs. At what point does it become significant? That's something that you would need to make in your mind. If it's really long pipes, maybe the turning resistance isn't significant because the pipe friction will be outclassing it. One point that I do want to make, though, is detailed T's can have convergence issues. This is due to just how complex they are. They're taking the velocity at each calculation, recalculating the resistance, and resolving your problem to make sure that the velocities did not change significantly. If you are using your detailed T's and you're having a convergence issue, you're absolutely welcome to send your model in to our support team. We'll look at it and help diagnose the issue with you. But one of the things that we often experience is if there's a convergence issue with detailed T's, we just change them to simple, and that is often a path forward. So if you're experiencing convergence issues, first try swapping them to simple T's. Orifices. These are kind of funny, kind of interesting little junctions. We also get this out of hydraulic resistance data. Comes up with these kind of fun equations that look really long. For simplicity's sake, though, it can be thought of as greater loss the more restricted the flow is. If we look at this kind of graph here, as the area becomes more constricted, the loss will become greater. We also have a round-edged option available. This is where you just simply put the inner diameter or the inner orifice dimensions. It will then determine the ratio between the upstream pipe and the orifice, and then calculate a K factor, a loss coefficient for that point. And as always, you can do user specified if you have, perhaps you have lab data for your specific orifice, and that is always going to be the most accurate. The data, the testing done on your unique component is going to be the most accurate data, and you can enter it. But if you don't have that data, you can use generalized equations such as this one. Screens, these are a fun one. They're going to be the same kind of long equation, similar loss model to the orifice, where the more restricted the area is, the greater resistance that will appear. And then we also included a few different screen standard options. Perforated plates, silk, a few different screen options available, and then, like I said, lab data for your specific component is going to be the gold standard, but there is pretty good resistance data already out for some of those things. Heat exchangers. You can also do hydraulic loss within your heat exchangers. They're shell and tube heat exchangers. These are a common setup. It's going to contain your length of pipes passing through the tank, and that tank is going to be filled with a secondary liquid source used to help with heat transfer. If you wanted to model those unique pipes within the heat exchanger, you can do that through the loss model tube configuration option. By default, it's going to use that Darcy-Weisbach pressure loss equation that we use for all of our regular pipes. You can also change the scaling percentage, such as those pipes are corroding over time or getting clogged up, such as blocked tubes. You can enter those values and it will calculate new loops accordingly. This can be very useful when you're trying to calibrate your model to a real system and approximate what is happening inside your heat exchanger. It might be not worthwhile for you to cut open that heat exchanger, and instead you can vary these two values and see at what point do you get an equivalent pressure drop. We have a few interesting case studies on that where customers will take that measured data, put it in, and take a Fathom model and continue to calibrate the Fathom model until they're pretty much the same data. And then they say, okay, this heat exchanger must be this corroded, this blocked, this something. And then use that to say when do things need to be maintained and when do things need to be replaced. So that was a lot of minor losses in junctions, but we want to give a little bit of love here to the minor losses in the pipes as well. Almost all the minor losses that we've just looked at that can be applied to these junctions can also be applied as fittings and losses within the pipe itself. These values, they come from Crane, Idlechick, Miller, Darby, all reputable sources within our industry. But it is very important to make sure that the fitting that they measured correlates well to what you are using. It needs to be an apples to apples approach, not apples to oranges. When you are inside the pipe property menu, you'll go to that second tab, fittings and losses. It will give you the option to add more fittings and losses. Press the button. It will bring up a new menu, the pipe fittings and losses menu, and you would swap between the different tabs and add a quantity accordingly for whatever will be inside that pipe. That's nice because then it means less junctions on your workspace and all that hydraulic loss is still accounted for within your pipe. Good thing to keep in mind is you can always make a user library to create and add system unique fittings and losses from data provided by manufacturers. And then it will be in these tables for you to add, as well as the junctions. All right, so now into some of those extra considerations that I promised. For something so minor, there's a lot of detail and minutia out there. There's a lot of things that need to be kept in mind, and we're not done yet. So let's look at some considerations such as how these minor losses are going to be impacted in laminar flow, how are these minor losses going to be impacted by compressible flow and transient flow within our aero and impulse products. Starting with the minor loss in laminar flow, the minor loss found in components is going to be greater in laminar flow than it is in its turbulent counterpart. One of the ways that we calculate and account for this is what we call the adjusted turbulent K factor, ATKF. And it's the method that we use to convert a K factor from the turbulent regions to the laminar regions. When you go to your analysis setup menu, you'll see a laminar and non-Newtonian corrections tab. Click that and you'll see whether you want to apply these corrections or not, as well as do you want it to be applied in turbulent regions or just in the improved laminar regions, and then you can even turn them on and off for particular junctions as well. The equation kind of used is pretty straightforward. It will take the K turbulent factor and it is going to then say what is the friction factor of your flow at your Reynolds number, at your pipe roughness, what is the turbulent friction factor at that fully turbulent region, and just correlate them to what the K factor will be in the laminar region. There's a lot of different opinions that exist in literature. If you went to the AFT help site, you can find greater discussion about ATKF, as well as different literature sources discussing whether minor loss corrections need to occur in that laminar region. Some say yes, some say no. We put that on you, the user, to know, is it significant enough for you to include. Aeroflow calculations. Aero calculates the flow within a pipe using two marching methods. That's because within compressible flow, the density is going to drop due to friction, increasing the velocity down the pipe to Mach. That's just inherent of internal compressible flow. So we use two different marching methods, and we can use them in tandem. One is called the length march method, where it will go an equal distance down the pipe and say, what is the Mach number? What should the Mach number be now at this length of the pipe? And continue to piecemeal them together. A second one is a Mach number march, where it will go down the length of the pipe for a single length or a single change in Mach number, and then until it gets to the end. And that's what we can see here. We can see a Mach number march where it goes from 0.26 to 0.27, goes from 0.27 to 0.28 between 1 and 2, 0.28 to 0.29, from 3 to 4, and we can see because the velocity is increasing down the pipe, that Mach number is increasing down the pipe, those regions become smaller and smaller and smaller. Kind of a fascinating thing about compressible flow. It will continue to iterate through these approaches until the pressures and flow rates are balanced, giving you a good calculation of what is the mass flow rate in your compressible flow problems. So what could be some issues here? Let's talk about minor losses in aero and compressible flow. We need to remember that the minor losses are calculated by the velocity. It is proportional to that dynamic pressure, that velocity component. So what does aero use for the velocity to calculate the minor loss? We know that the velocity is increasing along the pipe, so which is it going to use? It depends on how you set up your problem. If a junction is included inside or along the pipe, such as within your fittings and losses, aero will break it up into the pipe and say, add it as a sum average across this pipe. Instead, if you have your minor loss explicitly placed in a junction, such as a valve, what we see here, like we place it explicitly in this valve, aero will use the velocity calculated at only that point. So that's the key difference. Fittings and losses, it will be averaged out throughout the entire pipe using the different velocities along the way. And an explicit junction will use only the velocity at that point. Let's go look at an aero model. We have this aero model right here where I took this K, or this valve, found out the K is about 24 for it, and then I placed it either 10% down the pipe, so if this is a 40-foot pipe, pretty decent size pipe for if you're trying to do some sort of blowdown procedure. If we go 10% down the pipe and place the valve, if we go halfway down the pipe, place the valve, or if we go 90% down the pipe, place the valve, all three of these compared to what if we just include the valve as a fitting and loss. And the results were quite interesting. We can get to a point where the outlet Mach number as well as the mass flow rate are dependent on where do you put these components. That's because that resistance is going to be based upon that velocity. So we'll see here, if we're at about 0.95 Mach, if we put it halfway down the pipe, we could get sonically choking putting it further down. So how much does this change your results? You have to be the judge of that, but I do want to point out that ultimately what I'm trying to point out is where you place these junctions may have a significant impact on your results. Looking here at our fittings and losses, it is significantly it is under predicting whatever Mach number that the other three are showing, and it is under predicting the mass flow rate that these other three are showing. So when in doubt, explicitly model your junctions unless you truly know that it is irrelevant. That's the sign of a good, competent engineer. Know what is useful and not useful to include. So that's one of the things we encourage. We tend to say explicitly adding these junctions instead of fittings and losses will always produce the most accurate results to your system. So we encourage doing them. Let's look at the minor losses within impulse and transient flow. We can apply fittings and losses likewise in impulse that we would in Fathom, and it will likewise evenly disperse that K across the pipe. Where can the issues come from this? Reflections will occur due to the impedance of the flow. Like if we're dealing with our transient simulations, we know that reflections will come from those restrictions. If you have a valve that would reflect a significant amount of pressure back in the transient simulation, placing that valve into the pipe as a fitting and loss may lose a bit of that detail of those reflections. Reflections will still occur because it will be as the flow and pressure is going down the pipe, the impedance will reflect back at the different stations. So what can you, the user, do? In Aero, and especially in Impulse and any of our models, we say be as detailed as possible to get the most detailed results possible. So that means explicitly modeling these junctions in the Impulse workspace. However, Impulse has the extra trickiness of, if we're being very, very specific, we have lots of junctions and lots of details, our runtimes can become really large. As kind of a way, we kind of say, build it with as much detail as possible, and if the runtime is unagreeable with you, over hours long, then you can start simplifying it, because ultimately what you're trying to see is the pressure surge relation, not the hydraulics of the pressure drops. You're trying to see how is that wave moving through your system. So a simple way to combine things where they can, Impulse provides this for you. By going to your analysis setup menu, you can see the sectioning tab. From sectioning, there's this option on the right, join pipes and junctions, and it will tell you X number of junctions they don't have transient data applied to them. They can just be wrapped right into the pipe and decrease your calculation time. The trade-off being they might not reflect as well as if you had explicitly had them in your model. Once again, something that you would need to determine for yourself. So in short, minor losses can be quite significant, and us as responsible engineers, we need to know how significant can they be in certain situations. Not just, we don't need to just toss them out. We need to fully wrap our heads around the problem and say, do these have a significant impact, and do I need to model them in order to get as fine detailed results as I can? So I hope this gave you some food for thought. If you have any questions based upon this webinar or any other hydraulic loss questions, please send them to our webinars at aft.com email address. That will come to me, and I will be able to answer your questions. If you have future webinar suggestions, we're always looking for those topics, things that you, the customers, our users, are interested in. We want to provide that information to you. Please submit a topic to that same email address. And again, thank you for listening, thank you for watching, and I hope you have a blessed day.